Welcome to this presentation on interfaces and propellant formulations for lunar-based facilities. I'll introduce Ali Reichenberg and also David Brower, who's the president of Astra Technology. So first, Ali. Ali Reichenberg is an incoming aerospace engineering student at the University of Florida. She graduated high school from Austin High on the engineering pathway with a distinction from the Academy for Science and Innovation. She recently completed an internship at Astro Technology, where she supported engineering teams working on applied technologies for aerospace and energy systems. An Eagle Scout and active tutor through Mu Alpha Theta, Ali has developed strong leadership and communication skills through her involvement in Model United Nations, peer mentoring, and STEM outreach. This fall, she will begin her undergraduate studies in aerospace engineering at the University of Florida, with aspirations to contribute to the future flight and space exploration. And next, I'll introduce David Brower as well. He is the president of Astra Technology, a Houston-based engineering firm focused on innovative solutions for subsea monitoring, aerospace instrumentation, and structural health systems. With over 30 years of leadership at Astra Technology, David has overseen the development and deployment of groundbreaking technologies in extreme environments, from deep sea oil fields to aerospace applications. He holds a degree from the University of Utah and has been a driving force behind cross-disciplinary innovation, bridging material science, sensing systems, and applied engineering. Under his leadership, Astra Technology has collaborated with NASA, offshore operators, and academic institutions to advance monitoring systems that ensure safety and performance in mission-critical operations. And with that, I'll go ahead and turn it over to Ali for the presentation. Welcome, Ali.
Yeah, thank you, John, so much for the introduction. Let's jump right in. So, as you heard, my name is Ali Reichenberg. I'm a student at the University of Florida. I'm a researcher at Astra Technology, and I'm honored to have spent the last year working with John and David to bring you some exciting ideas today. So, one of the larger challenges of lunar settlement is the cost of transporting materials back and forth from the Earth's surface to the lunar surface. So, by using in situ resource utilization, we hope to limit these costs quite a bit. And there's two main ways that we've come to you to tackle this. The first one is lunar-derived propellants. And something that makes these unique is that they use little to no water in their designs because we want to conserve the water ice. Unlike water on Earth, once we use the water ice on the moon, it's just gone and it won't replenish itself. So instead, we are proposing that we mine the lunar rock for materials and use those materials. And additionally, these propellants will be used to transport material from the lunar surface to either lunar orbit or low Earth orbit. So we won't have to go through that Earth atmosphere. And our second proposal is a potential site for human habitats, which are lava tubes. So let's learn about some propellants. The first design we have for you is the end-burning aluminum rod matrix. This essentially is a bunch of pipe-like aluminum rods as our fuel with a LOX oxidizer. And this one is a conventional end burner, which means we'll have fairly stable pressure throughout. Additionally, because of this LOX oxidizer, startup and shutdown are simplified because when we have our LOX, we can start it. Without that, it'll stop. And that's also part of the reason it's safer to handle than many other engines. The second design is the cartridge-loaded hybrid propellant system. This one is a solid fuel instead of the last one. And something cool about it is that our powdered aluminum fuel and the silicon binder will both burn in the reaction, which is very unique. This will also need some sort of igniter. We would love to use some sort of hypergolic igniter to save costs. One of the important features of this is long-term storage. Because it can be made in advance, we can make many of these, set them aside, store them for long periods until we need them. And then very similar to the last one, we would also use LOX as an oxidizer, and it would simplify startup and shutdown through the amount of LOX we choose to put in, or if we choose to put in any at all. And it's safer to handle because without this LOX, we aren't going to be able to start up this engine. The third one is an aluminum LOX slurry. And you will notice that I made a point at the beginning to not use water in our designs, but this design uses an aluminum water mixture for the slurry. And there's two main reasons why we're comfortable doing that in this design. The first one being that because it's a slurry mixture, it'll use significantly less water than many other engine designs that prioritize it. And the second reason being that we don't want to use mainly lunar water as the source of the H2O. We would prefer to use the output from fuel cells on a lunar vehicle. So it would also help lighten that mass of the vehicle. Something special about this, it has a much lower combustion temperature because of that H2O, that water mixture inside, which would also provide cooling in addition to fuel. And similar to the others, it's a bit safer to handle than many other engines because of this LOX metering that we could use. And then the next one, and admittedly my favorite one, is the silane engine. This one would combine silicon and hydrogen to make silane, which we would have to manufacture on the lunar surface, but this substance is hypergolic. On Earth, a hypergolic engine might be more dangerous because our atmosphere is made of oxygen, so we would get that reaction immediately. But on the lunar surface, any oxygen coming into the engine would be oxygen we put there ourselves. So some important features of this, as I mentioned, hypergolic. This is super exciting. It'll simplify that startup and shutdown, and it will eliminate the need for an igniter. So rather than transporting an additional igniter and materials, we have all of the materials on the lunar surface and we don't need to transport an igniter. And the materials needed for this are very abundant in the lunar soils. Silicon and hydrogen and oxygen can all be found inside of those soils. All right, so I just introduced 4 different engine propellant formulations for you, all that use little to no water, and now let's talk about some habitation sites. Lunar lava tubes exist both on Earth and on the lunar surface, and these formed in the wake of volcanic eruptions. So differences in lava cooling time left massive underground caverns under the surface of both the moon and Earth. And on the moon, we've already found systems of these caves in the Mare Tranquillatus region. And so we already know that there's a whole system of these. And using GPR, we have evidence to believe that there's more of them, and we have a good way to find more of them. And there are many benefits listed on the slide, but we're going to get into those very shortly. So the first benefit is temperature control. When we're on the lunar surface, we get a wide range of temperatures, from below freezing to above boiling. And here's a little chart just showing 13 hours what this temperature range looks like. Meanwhile, lava tubes, they're stable year-round at 63 degrees Fahrenheit, which I don't know about y'all, but I live in Texas, so having an underground tunnel that's 63 degrees all year sounds like a dream. Another reason is radiation protection. On the lunar surface, we'll experience 0.11 to 0.38 sieverts per year, which is very dangerous for humans. But as we get deeper and deeper under the surface, we start to experience less and less of the effects of here. And here's a chart showing that. So when we get about 6 meters deep, the effects are almost negligible, and we don't have to worry as much about radiation. Additionally, once we get about 6 meters deep, impact protection becomes a feature, because small meteorites or debris or space dust going at high speeds won't be able to hit human habitats. So I've just explained a few different propellant formulations and some human habitats. But what is the reason for doing all of this? Why go to the moon in the first place? I'm going to give you a few reasons. The first one being cooperation. Going to the moon, creating these habitats, being able to create these complicated systems is not something one company or one place can do all alone. So hopefully by making our goal to have these missions, more people will collaborate, not just to help fund the projects, but also sharing research and ideas. And then the second one, though it's a bit more far out there, is helium-3 energy. Helium-3 naturally exists on the lunar surface and can be put into nuclear reactors to give us some very powerful but clean energy. So hopefully years down the line, we can create the facilities to manufacture this helium-3 to make low cost, high yield, and renewable energy in the future. I've introduced 4 different propellant formulations, all using little to no water. And I do want to mention again my favorite one, the hypergolic engine, because if we can limit material transfer in any way, including just getting rid of that igniter, then we're saving ourselves a lot of time and money. Additionally, lava tubes serve as a very promising habitation site or just a site for research, given their radiation protection, protection from impact, and temperature control. And if we all decide to work together on these types of projects, hopefully we can foster some more collaboration and get a new renewable energy source. I want to take a moment to thank John and David so much for their mentorship over the last year. It has been such an honor working with them. And if anyone has any questions about the project, please feel free to contact me or shoot me an email. Thank you so much for listening.
Well, thank you, Ali, for that insightful presentation, and appreciate the insights about propellants, motor designs, and also habitats.